In this video, we're going to complete the KutaSoftware Infinite Calculus free worksheet evaluating limits, and specifically evaluating limits at kinks and jumps. So we're going to be dealing with right-sided limits and left-sided limits. So right-sided limits are written as the limit of f of x as x approaches a from the right. So after the a superscript that's positive. That means that we're looking at the limit, and let's say that limit equals L. So the limit of f of x as x approaches a from the right means that we're looking for the limit coming from the right. So x being near a, those x values are going to be greater than a. That's coming from the right. So then left-sided limits then, we'll have the limit of f of x as x approaches a from the left. So that's going to be a negative superscript, and let's set that equal to L. That means that x is less than a. So we're looking at x values that are less than a as we approach a. In one case, we're looking at values within the domain that are greater than that point a, and then in the other case, the left-sided case, we're looking at values in the domain that are less than that point a to see where that limit is. And I want to note that the limit of f of x as x approaches a, that will equal L if and only if, and in this case L is some arbitrary value, so that will equal L if and only if both the limit of f of x as x approaches a from the right equals L and the limit of f of x as x approaches a from the left equals L. If one of those does not equal L, let's say the limit from the right, then the limit as x approaches a does not exist. So this is a very important note. But let's get started with number 1. In numbers 1 through 4, we're going to evaluate each limit. On number 1, our function is f of x, that's equal to 4x plus 4 over the absolute value of x plus 1. And we're evaluating that limit as x approaches negative 1 from the right. So coming from the right, so coming from x values that are greater than a. So x values that are greater than negative 1, that's all the values to the right of 1, hence a right-sided limit. So as we're coming from the right, we can see that we are approaching positive 4. So 4 is our solution in number 1. If this was a left-sided limit, we would be coming from values where x is less than a, so values less than negative 1. And as we approach negative 1, you can see that we're going to negative 4 for f of x. And because negative 4 does not equal 4, if we were to do the limit of the function as x approached negative 1 in general, that limit would not exist because 4 does not equal negative 4. However, in number 1, we were just looking at the right-sided limit, which has a value of 4. Let's move on to number 2. In number 2, we're looking at the limit of the function f of x as x approaches negative 1 from the left. So now we're coming from values where x is less than a, and that a value is negative 1. So coming from values where x is less than negative 1, looking at this piecewise function, that's going to be associated with the values in this first part for negative x minus 8. And you can see as we come from the left following that function, as we approach negative 1 in the x, we're approaching negative 7 for f of x. So negative 7 is our solution in number 2. Moving on to 3. For number 3, it does not tell us whether we're approaching from the right or the left, so we have to look at that limit from both the right and the left. So the limit as we're approaching negative 3 from the right. Here is where x equals negative 3. So as we're approaching that from the right, we are getting closer to the value negative 3. And as we're approaching from the left, we're also getting closer to the value negative 3. So because the limit from the right is negative 3, and because the limit from the left is negative 3, and negative 3 is equivalent to negative 3, then the limit as x approaches negative 3 does exist, and its value is negative 3. Let's look at number 4. In number 4, again, we're looking at the limit as x approaches negative 1, and this is generally. So we need to see if it approaches the same number from both the left and the right. So going from the left, we can see that as x approaches negative 1, for f of x, our limit is negative 1. And as we're approaching negative 1 in the x from the right, we're approaching negative 3 for f of x. So because negative 1 does not equal negative 3, the limit does not exist. And again, that's because my right-sided limits and my left-sided limit are not equivalent. Let's continue on to the second page. For numbers 5 and 6, it says to evaluate each limit, and you may use the provided graph to sketch the function. So let's look at number 5. We have the limit as x approaches negative 1, and that's going to be from the left, which we know are values where x is less than a. But before we jump into that limit, let's just graph this piecewise function. Each piece is a linear equation in the form of y equals mx plus b. So for our first, our y-intercept is negative 3, and our slope is negative 1, which I'll write as 1 over negative 1. Now this is true for values where x is less than or equal to negative 1. And right now we're at x equals 0, so we know this point is not included in this piece. So let's use our slope to find a point that is. So going up 1 in the rise and over 1 in the x, we'll get to x equals negative 1. And when we're at x equals negative 1, we're at negative 2 for f of x, and x is included in that. So I'm going to draw a line connecting those 2 points. However, I'm going to be excluding all the values after x equals negative 1. So I'm going to adjust my line and erase that first point I graphed. Another way you could have graphed was by using a t-table. So I have the first part of my function, now I'm going to look at the second part. In the second part, my y-intercept is 1, so we're at 0, 1, and I'm going to use my slope of 1 to find my next point. And let's go negative 1 over negative 1, because a negative over a negative is a positive. So I'm going to go down 1 in the rise and 1 to the left in the run to get to where x is equal to negative 1, but note that x cannot be negative 1, so this is going to be open circle around that point, negative 1, 0. And now I'll connect my points with a line. So here is my piecewise function graphed in number 5. Now in all honesty, I didn't even need to graph this because we're looking at the limit as x approaches negative 1 from the left. So that's x values less than a, or x values less than negative 1. So the piece that I'm looking at is the piece that represents those x values less than negative 1, which is negative x minus 3. So if I was to take negative x minus 3 and plug in negative 1 for x, I would have the opposite of negative 1 minus 3, which is a positive 1 minus 3, which gives me a negative 2. So negative 2 is my limit of f of x as x approaches negative 1 from the left, and that's because the domain for this part of the function represents coming from the left for my limit. And if you want to see that graphically, we can come from the left and notice that we're on that first part of the function coming from the left, and we're heading towards that f of x value of -2. Let's continue on to number 6. And for practice, let's try and calculate 6 without graphing. For number 6, we're looking at the limit as x approaches -2. So that means we need to calculate the limit from the right and from the left. So we're going to plug -2 in for each of these equations. So in our first quadratic, we're going to have the opposite of -2 squared minus 4 times -2 minus 5. The opposite of -2 squared is the opposite of a +4, which is -4, and then we're subtracting a -8, which is the same as adding +8, and then we're subtracting 5. -4 plus 8 is a +4, and when we subtract 5, that is equal to -1. And remember, this is the limit of f of x as x is approaching -2, our a value, from the left. Now, in order for the limit of f of x as x approaches -2 to exist, the limit coming from the right also needs to be equal to -1, which we can see is true because f of x is equal to -1 for all values where x is greater than -2. So because it's a constant, -1 is the limit for all values where x is greater than -2, f of x equals 1. So that means that -1 is indeed the limit of f of x as x approaches -2 from the right. So because -1 equals -1, because that limit of f of x as x approaches -2 from the left is equal to the limit of f of x as x approaches -2 from the right, because those are equal, the limit as x approaches -2 is -1. But let's graph and double check. Let's graph that second half first. We know that for values where x is greater than -2, we're at -1. So we'll find -2 in the x, -1 in the y. That will be an open circle, and then a horizontal line continuing on in the positive x direction after that. Now, for that first piece, -x squared minus 4x minus 5, that's going to be a quadratic, and I'm going to plot a few points in order to draw the curve. However, we know one point is -2, -1. So now I'm going to actually fill in that circle because that is true for values where x is less than or equal. So let's go ahead and plug in another value where x is less than or equal to -2. Let's plug in -3. So I have the opposite of -3 squared minus 4 times -3 minus 5. So that's the opposite of a +9 minus 4 times -3 is a -12, so that's going to be -9 plus 12 minus 5. -9 plus 12 is a +3, and 3 minus 5 is a -2. When I'm at -3 in the x, f of x is equal to -2. And now I'll plug in -4. So we'll have the opposite of -4 squared minus 4 times -4 minus 5. So that's the opposite of -4 squared is going to be -16. And then when I'm subtracting 4 times -4, that's the same as adding a +16, and then I'm subtracting 5. -16 plus 16 is 0, minus 5 is -5. So when I'm at -4 in the x, f of x is -5. Now, I can go ahead and attempt to plot another point, but I know that once I go to -5, I will no longer be able to enter in my y value on this graph. Therefore, I'll just go ahead and draw my curve now, connecting my points. So again, the limit of f of x as x approaches -2 is -1, because that limit of f of x is -1 as x approaches -2 from both the right and left. Let's continue on to the next section. For numbers 7 through 12, we're evaluating each limit. So in number 7, we're evaluating the limit of f of x as x approaches 0 from the right. So remember, that's for x values that are greater than that a value, where a in this case is 0. And that occurs in this second piece. So I'm going to enter in 0 into that second piece. So I'll have the opposite, or negative 0 squared plus 4 times 0 minus 3. 0 squared is 0, 4 times 0 is 0, so I'm left with a negative 3. So my limit of f of x as x approaches 0 from the right is negative 3. Now, on to number 8. In number 8, we have the limit of the absolute value of x over x as x approaches 0 from the left. So I think the easiest way to do this, unless we want to use a graphing calculator, is with a t-table. So I'm going to enter in values of x and f of x. However, I'm going to use values coming from the left. So that's for x less than 0. So I'll do negative 1, negative 1/2, and I'll go ahead and do negative 1/4. Entering in negative 1, we'll have the absolute value of negative 1 divided by negative 1. The absolute value of negative 1 is a positive 1, so that's 1 over negative 1, which equals negative 1. For negative 1/2, we'll have the absolute value of negative 1/2 all over negative 1/2. The absolute value of negative 1/2 is a positive 1/2, and as opposed to dividing by negative 1 over 2, I'll multiply by a negative 2 over 1. So I'm multiplying by that reciprocal. So that's going to be negative 2 divided by 2, which is a negative 1. And then I'll look at negative 1/4. So I'll have the absolute value of negative 1/4 all over negative 1/4. So the absolute value of negative 1/4 is a positive 1/4, and as opposed to dividing by negative 1/4, I'll multiply by that reciprocal, so multiplying by negative 4 over 1. Negative 4 divided by 4 is a negative 1. So you can see, as I'm approaching 0 from the left, my limit is negative 1. So negative 1 is my solution in number 8. Now on to number 9. In number 9, I'm looking at the floor function, so we're rounding down for values between integers. And we're looking at this as x approaches 0 from the right. So that's coming from the direction where x is greater than 0. So again, I'm going to make a t-table, x and f of x values. Coming from the right, I'll go from 1 to 1/2, and I'll go ahead and use 1/4 again as well. So you can see my x values are decreasing, so I'm approaching 0, but I'm coming from the right, so coming from that positive direction. So first, I'll have the floor of negative 2 times 1 plus 1. Negative 2 times 1 is negative 2 plus 1, so that's going to be the floor of negative 2 plus 1, which is negative 1. And rounding down negative 1, I'll get negative 1. Now let's look at 1/2. So that's going to be negative 2 times 1/2 plus 1, and that entire quantity rounded down. So negative 2 times 1/2 is a negative 1, and negative 1 plus 1, rounding down, that's going to be the floor of 0, which is 0. Now let's look at 1/4. We'll have negative 2 times 1/4 plus 1, rounding that down, negative 2, so I'll have negative 1/2 plus 1. Negative 1/2 plus 1 is going to be a positive 1/2. I'm rounding that down, that's going to be 0 as well. And just to double check, let's put in one more point. Let's do 1/8. So we have negative 2 times 1/8 plus 1, and we're rounding this down. Negative 2 times 1/8 is going to be negative 1/4, and we're adding that to 1. That's going to give us a positive 3/4, which we're rounding down to 0. So as we're approaching 0 from the right, we're approaching 0 for f of x. So 0 is our solution in number 9. Let's move on to number 10. In number 10, we have the limit of f of x as x approaches 1. So we need to double check this from both the right and left. So we'll start by plugging 1 in for this first piece, and then we'll plug 1 in for the second piece and see if those limits are equal. So plugging it into the first piece, we'll have 1 over 2 plus 9 over 2, which equals 10 over 2, and 10 divided by 2 is 5. So coming from the left, we're at a positive 5. Now let's check coming from the right. Plugging 1 in for x, we'll have 1 squared minus 6 times 1 plus 10. 1 squared is 1. We're subtracting 6 and then adding 10. 1 minus 6 is negative 5. Negative 5 plus 10 is positive 5. So because 5 equals 5, my limit as x approaches 1 is 5 for number 10. For number 11, I'm finding the limit of 3 times the absolute value of x plus 1 over x plus 1 as x approaches negative 1. But let's look at this function and feel free to graph it if necessary. We have 3 times the absolute value of x plus 1 over x plus 1. Now what really changes these values is when the absolute value is equal to 0. So because this is approaching negative 1, we need to double check from both the left and the right. So we'll have x, f of x, and I'll check these for when x is approaching negative 1 from the left. So I'll enter in negative 3 and negative 2, and I know that negative 1 will be 0 in the denominator, which we cannot divide by a 0. Then I'll go to negative 1.5 or negative 3 halves. And then I'll look at this function coming from the right. So I'll go from 1 to 0 to negative 1/2. So here we're coming from the right, and there we're coming from the left. So these limits need to be equal in order for the limit as x approaches negative 1 to exist and have a value. So let's plug in numbers and solve. Plugging in negative 3 for x, we'll have 3 times the absolute value of negative 3 plus 1 all over negative 3 plus 1. That gives us 3 times the absolute value of negative 3 plus 1 is the absolute value of negative 2, which is a positive 2. So 3 times 2 all over negative 2. 3 times 2 is 6. 6 divided by negative 2 is a negative 3. Now for negative 2, we'll have 3 times the absolute value of negative 2 plus 1 all over negative 2 plus 1. So we'll have 3 times the absolute value of negative 2 plus 1, the absolute value of negative 1, which is a positive 1, and that's all over negative 2 plus 1, which is negative 1. So we'll have 3 over negative 1, which is negative 3. Now we'll look at negative 3 halves. We'll have 3 times the absolute value of negative 3 halves plus 1 all over negative 3 halves plus 1. So that's going to be 3 times negative 3 halves plus 1 is negative 1/2, but the absolute value of negative 1/2 is a positive 1/2, and we're dividing that by negative 3 halves plus 1, which is negative 1/2. 1/2 divided by negative 1/2 is a negative 1. 3 over negative 1, or 3 times negative 1, is negative 3. And now from the positive direction. If we plug in 1 for x, we'll get 3 times 2 over 2, which is 3. Now if we were to enter in 0, we'll have 3 times 1 over 1, which is 3, and entering in negative 1/2, we'll have 3 times 1/2 divided by 1/2, which again is 3. So our limit is positive 3 from the right and negative 3 from the left. Therefore, because those limits are not equal, the limit as x approaches negative 1 of the function 3 times the absolute value of x plus 1 over x plus 1 does not exist. Now moving on to number 12, we have the limit of f of x as x approaches negative 2. So we're going to look at it as it approaches from the left and as it approaches from the right. If those are equal, then the limit exists and has a value. So plugging -2 in for the first piece, that's going to be -2 squared, which is 4. Now plugging -2 in for the second piece, that's the opposite of -2 over 2 plus 3, which -2 over 2 is -1, and the opposite of -1 is +1, so that's 1 plus 3, which equals 4. So because 4 equals 4, the limit exists, and the limit is 4. Now onto the critical thinking questions. In number 13, it says, give an example of a two-sided limit of a piecewise function where the limit does not exist. Well, this one's rather easy. We could just rewrite problem number 4, because that was a piecewise function of a two-sided limit where the limit did not exist. However, let's come up with a new example. Let's have the limit of f of x, and let's do this as x approaches a +1. And we're going to see, so I'm going to have f of x be the piecewise function. Now, as x approaches 1, I want to have different values for my function coming from the left as opposed to coming from the right. So I'm going to have x less than 1 as the domain for one piece, and x greater than 1 as the domain for my other piece. And I'll just make this greater than or equal to 1. So for values less than 1, I want the limit to be different than values greater than or equal to 1. So this is easy. Let's just do two completely different constants, 0 and 2. If I do 0 and 2, approaching from the left, my limit is 0. Approaching from the right, my limit is 2. Because 0 doesn't equal 2, the limit as x approaches 1 doesn't exist. Or we could put in x, because if we were to plug in 1 for x, the limit from the left would be 0, and the limit from the right would be 1. So that's just an example of a two-sided limit of a piecewise function where the limit does not exist. So go ahead, get creative, and leave your example in the comments below. In number 14, it says to give an example of a two-sided limit of a function with an absolute value, so there needs to be an absolute value somewhere in the function, where that limit does not exist. So, for example, number 11, approaching from the right and approaching from the left gave us different values for the limit, therefore the two-sided limit did not exist. But let's look back up at number 8. For number 8, we had that the limit as we approach 0 from the left was -1. Well, let's see what happens when we approach 0 from the right. So the limit of the absolute value of x over x as we approach 0 from the right, let's plug in values coming from that right, so where x is greater than 0. So I'll do 2 and 1 to start. So that's the absolute value of 2 over 2, which is +1, and that's the absolute value of +1 over +1, which is 1. So you can see that limit, we can plug in another number such as 1/2. +1/2 divided by +1/2 is 1. So that limit is 1. So the limit from the left is -1, and the limit from the right is +1. So back down to number 14, our example, I'll write the limit as x approaches 0, meaning from both the right and the left, of the absolute value of x over x. Because as we approach 0, from one side we're at -1, and from the other side we're at +1. And because -1 does not equal +1, that limit does not exist. And that wraps up the Evaluating Limits at Kinks and Jumps worksheet. If you have any questions or had further answers to the critical thinking questions, put them in the comments below. And if you want to support my channel, do so by liking and sharing this video and subscribing. And if you want further information, go to maemap.com, maemap.com.